Hey everyone, I hope you're doing well today. In this video, I'm going to try to simplify down polynomials for you. For this particular video, we're going to look at this function of f of x is equal to x to the fourth power minus 4x cubed plus 8x minus 32. Since the highest degree of this polynomial is to the fourth power, this is a quartic polynomial. For this polynomial, I'm going to cover the factors, the zeros, also known as the roots or the solutions, the x-intercepts, the y-intercept, and the graph. At this point, hopefully you already know how to factor quadratic functions, whether you learned it by factoring, completing the square, or using the quadratic formula. The challenge with this polynomial though is that it's raised to the fourth power, not raised to the second power. Our goal is to break this scarier looking polynomial down into some smaller pieces so that we can actually factor it using quadratics. Let's see if we can rewrite this polynomial into some smaller factors or smaller pieces so we can understand what's going on with it. Let's start by writing the possible rational zeros. To do that, we're going to want to identify our p-value, which is our constant of negative 32, and our q-value, which is our leading coefficient of positive 1. Remember, the list of all the possible rational zeros for a function is going to be the ratio of the p factors to the q factors. Dividing all the factors of negative 32 by all the factors of positive 1, we're going to get these 12 factors. If this polynomial has any rational zeros, they have to be on this list. At this point, you just want to pick one of these rational zeros on the list and see if it's going to be a zero. While you may pick a few that don't work at first, eventually you're going to find one. Now, to actually find the rational zero, we're going to have to take turns picking some of these off this list and trying them out until we get a remainder of 0. If none of them work, that just means that none of the zeros are going to be rational. I think it's pretty safe to say though that one of these will work though, or else we won't be able to talk about this polynomial very much. So while you might not always pick one that works the first time, for this video I'm picking ones that I know are going to work. So I pick negative 2 off the list, and I'm going to go ahead and write the coefficients for a polynomial, which are going to be 1, negative 4, 0, 8, and negative 32. Make sure you add in that 0 there because there's 0x squared. We need that for a placeholder. Since we got a remainder of 0 at the end, we know this negative 2 is a solution, so we know that one of the factors is going to be x plus 2. As for these numbers at the bottom of 1, negative 6, 12, and negative 16, we can go ahead and use them to try to find another solution and factor. This time, picking another possible rational zero of 4, let's give this one a try. We're testing out 4, and we're going to write the coefficients of 1, negative 6, 12, and negative 16. Once again, we can see that the remainder is 0, so that 4 is a solution and x minus 4 is going to be a factor. Keep in mind that this part of the process of synthetic division may take you a little longer because you're not going to get them necessarily right on the first try. So we found two rational zeros of negative 2 and positive 4, so let's take a look at these leftover numbers of 1, negative 2, and 4. These numbers here represent the coefficients for our leftover polynomial of 1x squared minus 2x plus 4. This right here is a quadratic polynomial, and to see if we can factor it, we can check the discriminant, which is the square root of b squared minus 4ac. Given that a is 1, b is negative 2, and c is positive 4, we're going to get 4 minus 4 times 1 times 4, and that's going to be 4 minus 16, and that's a square root of negative 12. Because the discriminant is equal to negative 12, we know that this polynomial of x squared minus 2x plus 4 is not factorable. So let's just take a pause right there and see what we've done so far. At the top here, you can see that this was the original function that we had from the start. After we found out that negative 2 was a 0, that meant that x plus 2 was a factor, and it was going to multiply by this x cubed minus 6x plus 12x minus 16. Using our leftover numbers, we tested out another possible rational zero 4 and found out that it worked, so that meant that x minus 4 was also a factor, but we still had this quadratic of x squared minus 2x plus 4. And while we did find out two linear factors of x plus 2 and x minus 4, it turns out that this x squared minus 2x plus 4 isn't factorable. However, just because it's not factorable, it doesn't mean that we can't find the solutions. Completing the rest of the quadratic formula, we can find out here that our two other solutions here are going to be x is equal to 1 plus I root 3 and x is equal to 1 minus I root 3. If you want to write this as a factored form with these complex roots, this is what it would look like. So while we do have two real solutions, we also have two complex solutions. So for our factors here, we have x plus 2, then we have x minus 4, then we have x minus the quantity of 1 plus I root 3, and then finally we have x minus the quantity of 1 minus I root 3. This is what our original polynomial looks like in factored form. Now that we know the factors, we can go ahead and write the zeros, aka the roots or the solutions. From each of our factors, we can see that our solutions are going to be negative 2, positive 4, 1 plus I root 3, and 1 minus I root 3. Two of these solutions are real, and two of them are complex. From one of our real solutions of x equals negative 2, we know that we have an x-intercept of negative 2, 0, and from our other real solution of x equals 4, we have another x-intercept of 4, 0. For a y-intercept, that's always just going to be our constant, so that's going to be at 0, negative 32. When you plug in 0 for x in the polynomial, y, or f of x, is equal to negative 32. Because these types of polynomials are difficult to sketch, here's what it should look like. To go a little further, let's take a look at all the possible zeros that we could have had. If you look at the original function, you can see that between each of the terms, there are a total of 3 sign changes, from positive to negative or negative to positive. If we have 3 sign changes, we're going to have either 3 or 1 positive real zeros. To find the total possible positive real zeros, it's always going to be the number of sign changes minus 2 until we get to 0. So since 3 minus 2 is equal to 1, we could either have 3 or 1 positive real zeros. Then, looking at f of negative x, there's only one sign change, so we can possibly have one negative real zero. Let's look at this on a chart together. From looking at the sign changes for f of x, we knew that there could possibly be 3 or 1 positive real zeros. And from looking at f of negative x, we knew that there really could only be 1 negative real zero. And since we were given a quartic polynomial or a 4th degree polynomial from the beginning, we knew that there had to be a total of 4 zeros from the beginning. If the positive, negative, and complex zeros have to add up to 4, that means that there could be either 0 complex solutions here or 2 complex solutions here. And based on all the hard work that played out earlier, we knew that this second scenario played out. Our positive real zero was x equals 4, our negative real zero was x equals negative 2, and our 2 complex zeros were x equals 1 plus I root 3 and x equals 1 minus I root 3. And now you know a whole bunch of different information about this polynomial that you may or may not have wanted to know. Either way, I hope you found this video helpful, and if you want to help support the channel, please consider giving the video a thumbs up, and as always, keep up the great work.